In this recording, I am going to cover the topics from Chapter 8 on tectonics, earthquakes, and volcanism. So here's a list of the topics in the chapter. I'll briefly touch on the span of geological time, Earth's history and interior, a little bit more emphasis on the rock cycle and plate tectonics, then moving on to seafloor spreading and subduction zones, including plate boundaries, and then I will talk about deformation, folding, and faulting. I will wrap up with earthquakes, volcanoes, and mountain building or orogenesis. So here are some concept questions, and these may appear on your midterm. Please consider, as you review the reading material and lecture, what are Earth's history, interior structure, and materials? How does it all fit together in a big picture? How does plate tectonics explain changes in Earth's surface? And how do the plate motions affect Earth's crust? So Earth is roughly 4.6 billion years old, and the Moon is 30 million years younger. This has been determined by rock carbon dating with samples that were brought back from Moon explorations. And the Moon formed when a Mars-sized object struck the Earth and pushed off a chunk of the Earth into what is now our Moon. And when we talk about geological timescale and a summary of all of Earth's history, we talk about eons, which are very vast, briefer eras, periods, and epochs. And we use units like millions of years in order to describe geological time. There are major time intervals that mark the 5 mass extinction events, and these were time periods when the numbers of living species occurring at that time dropped dramatically. So here is a depiction of the mass extinctions shown with those red lines, and you don't need to be responsible for memorizing all of the names of them, but be aware of the occurrence of these extinctions and the disappearance of relatively different types of species. And an interesting and hopefully shocking and disturbing fact is that some scientists say we are on the brink of the next mass extinction caused by climate change. And we may be experiencing another mass extinction due to the alteration of our planet's conditions. So the concept of absolute time means the actual number of years before present, and then relative is how things are related to each other. So a sequence of events and what happened in what order. The scientific methods that determine these times are radiometric or carbon dating, and they can determine absolute age. Relative dating is based on the relative positions of the layers of rocks, which we'll see later in this presentation, above or below each other. And that's a vocabulary term called stratigraphy. With the principle of superposition, we know that rock and sediment are always arranged with the youngest beds superimposed toward the top of a rock formation and the oldest at the base. And that makes sense because if you dig up a rock, the oldest would be at the base or the bottom of your sample. And that's if they have not been disturbed or had their orientation changed. So here is a graphic representation of superposition, and you can see all of these different layers of rocks that are labeled and shown in the drawing according to the time period from when that rock material would have been laid down. So at the very bottom is the Precambrian, all the way up to the top in the blue in our diagram is Permian. And this corresponds to the photograph in A of the Grand Canyon, and this was formed as the Colorado River actually eroded a plateau in northern Arizona, and it exposed these colorful rock layers, which are easily seen in this image. So the principle of uniformitarianism is it's the present is the key to the past. So by looking at rocks and samples that we can collect today, we can study physical processes that have been active and operating throughout geological time. So again, another example, you can see different layers in this image. You can see rocks that are sliding down the mountain and look like a landslide, and deposition down at the bottom of the riverbed, and the water flowing through. And these different layers and different features represent millions of years of Earth processes. So Earth was condensed from a nebula of dust, gas, and icy comets about 4.6 billion years ago. Western Australia has the oldest discovered rocks, and the internal energy source of Earth is heat that is left over from the planet's formation, and it is primarily attributed to the decay of radioactive isotopes. Earth's core and magnetism, if we divide up the Earth and take an imaginary cross-section of it, we have a solid iron inner core and a molten or melted iron in the outer core. But the core is dense and metallic, both inner and outer. And the rotation of the Earth affects the fluid's outer core, and this is where we have the magnetic field generated. So here is a picture of that hypothetical cross-section. So in A, we have a representation of the Earth with that shape cut out of it. In B, you can see the different layers. And so we have the inner core and then the outer core represented as red to indicate that it is molten or melted. We have the lower mantle, upper mantle, and above that we have the asthenosphere, and then the lithosphere, and finally the crust, which we see on the surface of the Earth. And then if you look at C, it is taking another cross-section and showing the difference between continental or land crust and oceanic crust. And then we have our uppermost mantle, which is rigid, and our asthenosphere, which is plastic. So we don't mean the plastic like you would have in a water bottle. Plastic in this case means that it is movable and bendable and in constant motion or flux. Here is a depiction of that magnetic field that is caused by the movement of the Earth, and the Earth has geographic poles and magnetic poles. So a magnetic field draws a compass needle to point to magnetic north, as shown in A. And then you can see the magnetosphere depicted in the artist's drawing in B, and this protects the Earth from solar wind and cosmic radiation. So it actually repels those types of electromagnetic energy. And the magnetosphere encircling Earth is the strongest of all of the solid planets. Earth's mantle is a layer of hot and solid material, and this is 80% of Earth's total volume. It's composed primarily of the minerals iron, magnesium, and silicates. The warmer lower mantle rises upward and slowly cools. As it cools, the density increases and then the rocks begin to sink. So there are convection currents that power the process of plate tectonics. Here is a representation of that movement or convection current, and the arrows are indicating the directions of movement within the outer core and mantle, and moving up into the asthenosphere. So the rocks in the warmer and less dense inner mantle rise upward, where they slowly cool as their heat is transferred to the outer mantle. Earth's mantle is closer to the surface, the temperature and pressure decline, and rocks are more rigid. The asthenosphere lies below the lithosphere and extends from about 70 kilometers to approximately 250 kilometers. Again, geologists describe this as plastic, meaning it's weak and it bends slowly over long periods of time. Folding, faulting, and deformation of surface rocks are possible because of this plastic or bendable nature. Earth's lithosphere and crust are the uppermost layer of the mantle and crust. It floats on the asthenosphere and it's broken up into plates. These are called tectonic plates. The Mohorovic discontinuity, or moho, separates crust from the mantle, and then above the mantle lies the crust, and this is the rocky shell of the continents and ocean floor. The rock cycle is comprised of both internal and external processes. The landforms are created by internal processes, and weathering and erosion, which are external processes, reshape those landforms. All of this together is what is known as the geological cycle. So this diagram is showing you the geological cycle broken up into hydrological, or water, rock, and tectonic cycle. So if we start with the lower right hand corner of this image, we have the melting of the asthenosphere, and due to intense heat and pressure, we have rising of magma up through the volcano that is portrayed here. On the way in between the asthenosphere and the crust, we have the rock cycle metamorphic phase, and this is caused by, again, heat and pressure. Once we have rocks expelled, or spewed to the surface, we have them exposed to weathering, mass wasting, erosion, and transport. The blue arrows are showing you that after the weathering, mass wasting, and erosion, the transport is always downhill by the force of gravity, and we have sediments accumulating on the shoreline. And underneath the water is a process of lithification, which is cementing of rock and biological or living material. Then we continue on down into subduction, where one plate is going underneath another, and you can follow those arrows back down to where we started. The hydrological cycle, which we've studied in a previous chapter, involves the evaporation of water primarily from the oceans, transpiration from plants on the land, and then precipitation. And this movement of water and influence of solar energy contributes to the weathering, mass wasting, and erosion. And then finally, in the lower left-hand corner is a depiction of seafloor spreading. The arrows are indicating that this is a point of divergence, and that upwelling magma is coming up and cooling, and then it is moving in different directions at this divergent plate, and ultimately Earth's heat comes from radioactive decay in the asthenosphere. So finally, the tectonic cycle involves processes of plate movement, seafloor spreading, crust formation, subduction, and mountain building. The subcycles within the geological cycle that we just saw in that diagram, again, are the rock cycle, the tectonic cycle, and the hydrological cycle. Please make sure you review these vocabulary terms and understand how they all work together. So here is an example of different layers of rocks that you can see, and you can see evidence of erosion taking place on these physical landforms. Here's an example of the rock cycle showing that magma comes up at the bottom, and through the process of cooling and solidification, it is turned into igneous rock. Igneous rock is turned into sediment through weathering, erosion, transportation, and then the deposition at lower elevations, usually near or below sea level. Then we have compaction, cementation, and chemical actions. This is all known as lithification, and this is a hardening of that sediment into sedimentary rock, which has many layers. And then finally, the process of heat and intense pressure, or metamorphism, creates metamorphic rock. So the rock cycle is a natural recycling process, and the rocks form and change and reform into another type of rock. The elements that are the most prominent on Earth are the minerals oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. That makes up 98.5% of Earth's crust by weight. So a mineral is an inorganic natural substance with a chemical formula and usually a crystalline structure. A rock is an assemblage of materials, including these minerals and other types of organic matter. So So the three main pathways of the rock cycle, which we saw in the diagram, are contributing to produce igneous, sedimentary, and metamorphic. Igneous melts under high temperature and pressure, and there are two types of igneous: intrusive and extrusive. The latter, extrusive, comes from volcanic activity, and intrusive forms from mantle material injected into the crust, where it cools and hardens beneath the surface. Sedimentary comes from eroded rocks or sediments. They get deposited at low elevations and compacted to form new rocks. Two main processes contribute to this: chemical, materials dissolve in water, and organic, the decaying of living things compacts into the sediment. And then metamorphic, any rock that chemically reform under tremendous pressure and accompanying heat. So with the igneous process, we are considering magma, which is molten rock, and it contains dissolved gases. Lava is magma that reaches the surface. Magma intrudes into coastal rocks to form intrusive rocks. Magma extrudes as lava onto the surface to form extrusive rocks. The texture depends on the size of the crystals, and that size is directly related to how the rocks formed, whether or not they were slow or fast cooling. So here are examples of three different types of rock: granite, basalt, and rhyolite. And I will leave you to make sure you match up which is metamorphic, which is sedimentary, and which is igneous. So igneous process, with a slow cooling intrusive igneous rock, it will form a pluton. Multiple plutons larger than 40 square miles compose a batholith. These, exposed by erosion and uplift, can form the core of mountain ranges such as the Sierra Nevadas in the western portion of the United States. Igneous rocks make up 90% of Earth's crust. With continental crust, it's light-colored, low density. Think of granite. And oceanic crust is dense and dark-colored. Think of basalt. Sedimentary processes most form when eroding fragments of existing rock or organic materials are transported downslope by the forces of water, ice, wind, and gravity. Here is an example of how the feature that you see in B would have formed. So eroded sediments are transported down to the water level by flowing water and gravity, and they begin to settle. This is called sedimentation, step 1. In step 2, we have compaction, and over time, more layers pile up and press down the lower layers. Number 3, more layers or strata and further compaction forces out water from the layers. So now we've got the weight of the layers pushing down, and then finally in 4, salt crystals glue the layers together. This is cementation, and this is how sedimentary rocks are formed. So sedimentary process can be clastic, when you have a process of overlaying layers, cementing and hardening. You can also have organic processes from the shells and skeletons of marine organisms and the decayed remnants of plants. Chemical sedimentary rocks in marine and salty or saline inland seas. Some minerals separate from the water to form solid sedimentary deposits. Calcium carbonate forms from limestone and from inorganic sources. Water evaporates and it leaves residues of salt. This is where we get sodium chloride, which is table salt, and potash. Sedimentary rock strata is layered sedimentary rocks. The oldest will be on the bottom and the youngest layer on the top, and this gives us clues to past environments. So any rock can become metamorphic through intense heat and pressure that alters the chemical and physical properties. In general, it makes them harder and more resistant to weathering. There are different types of metamorphism: regional, is rocks buried inside crust, subjected to high temperatures and pressures over millions of years. Contact is when magma rises to the surface and it cooks the nearby rocks by touching them. Foliated are thin wavy lines of layers, and non-foliated is a crystalline structure, marble from limestone and quartzite from sandstone. So here are some diagrams related to the rock cycle. So in the top, it's showing increasing heat and pressure. And in B is contact metamorphism, and the intense heat is contacting and affecting the rocks that it touches. In C, here is an example of foliated rock, and then down in E, we have an example of non-foliated rock. And the rock that is used to make India's Taj Mahal has withstood the elements for over 360 years. Alfred Wegener was a scientist, and he came up with the hypothesis to explain the continental puzzle, or the fitting together of the plates. The continents moved together by the end of the Paleozoic era. It formed a supercontinent Pangaea. It began to break up at the beginning of the Mesozoic era, and with continental drifts, the continents moved slowly across the seafloor. So here are some artists' renditions of what the world would have looked like 220 million years ago, then 135 million years ago, and finally the continents that we would see today from a satellite are depicted in C of figure 8.13. So how do we know that this is plausible or possible? Plant and animal fossil records of organisms that could not travel across ocean basins match exactly on the edges of continents. And when it was first proposed, many people rejected it at the time. There was no how to explain it, meaning we didn't have the scientific ability and tools in order to compare these fossil records, but we do now. So here's some examples of fossils that have been found on 2 or more continents. So you can see the Cinognathus is found in Africa and South America, which are no longer touching. And you can see that the fern, represented by the green polygon here, is found in South America, Africa, India, Antarctica, and Australia. It's found on all of those continents, and the spores or the seeds would not be able to travel across the ocean basins that we have now. So that's evidence that these different land masses were indeed at one time touching. So since the 1950s and 1960s, scientists have built upon this theory. The lithosphere is divided into plates that float on top of the asthenosphere. These boundaries create new crust, mountains, and the seismic activity that we know as volcanoes and earthquakes. Lithospheric plates are enormous and unevenly shaped slabs of outer crust and upper mantle. There are at least 14 plates described at the present time. Here's the name of the plates shown in different colors, and you can see the different types of boundaries with different symbols. You can see subduction zones, spreading centers, and you can also see the plate motion depicted by arrows. So the theory of plate tectonics, tectonic is a word meaning building, and it refers to the changes in the configuration of Earth's crust as a result of internal forces. These forces are the upwelling of magma, the lithospheric plate movements, seafloor spreading, and subduction. These create and destroy seafloor. The effects that we study and experience are earthquakes, volcanoes, and then the deformation of the lithosphere, warping, folding, and faulting that lead to mountain building. So here is a diagram showing you how energy from the mantle is driven up, represented by the yellow arrows, and you can see the movement of the lithosphere shown with blue arrows here. This is the mid-Atlantic ridge. It is an area of seafloor spreading in between South and North America, and the continent of Africa. Evidence of this is shown in the photo that you see here. See, it's a rock-walled valley in Iceland, and it is a part of the zone where the two plates meet. In the middle, we have a representation showing you how this mid-oceanic ridge looks like the seam of a baseball, and so there is quite a complex set of physical factors contributing to this boundary. Seafloor spreading is given us insight into ocean floor, and it helped establish the continental drift theory. So along with dating and comparing fossils and other organisms, we now know that mid-ocean ridges or spreading centers are where divergent plate boundaries are moving plates away from each other. There are cracks in the lithosphere where the plates move apart, and the pockets of magma rise up. As they spread, more magma rises up to fill that void, and this creates new ocean crust. We can age ocean crust, and overall seafloor spreading builds mid-ocean ridges and drives continental movement. You can see in A that there is upwelling magma, and the arrows there are showing you the movement of those plates, and new rock is being formed with older rock closer to the edges of the continents. If you look at C, the overall map, it's showing the age of the seafloor in millions of years, with the younger areas being represented in reds and yellows, and the older seafloor in the blues and purples. So if you look carefully, you can notice along the mid-Atlantic ocean ridge that the young seafloor is in the middle, and then the older seafloor in terms of millions of years is along the coasts. Geomagnetism is also evidence for seafloor spreading. It's the study of the phenomenon associated with Earth's magnetic field. As lava erupts along a mid-ocean ridge, magnetic particles cool and orient toward magnetic north. This creates ongoing magnetic record of Earth's polarity. Over time, magnetic poles do reverse, and nowhere is Earth's seafloor more than 200 million years old because of the cycle of building and then tearing down that seafloor. Subduction zones are deep ocean trenches. This is where lithosphere formed along ridges sinks down, and then when the denser oceanic crust hits the lighter continental crust, it slides beneath, forming a subduction zone. So some diagrams for you to study. You can come back and look at these. There are major seafloor spreading and subduction zones off of the coast of Alaska. The Aleutian Islands are part of that, and you can see pictures here of Mount Augustine and also part of the North American plate in Icy Bay, Alaska. So the mechanisms or the way that things work with plate motion, there's a ridge push. A mid-ocean ridge pushes the plate away from the ridge, or a slab pull. Near the trench, gravity pulls the plate downward. So here are representations of a ridge push away from that center of convection, or a slab pull where the slab is actually being pulled down into the center of the Earth. There are interactions at plate boundaries. The three main types are divergent, plates pull apart; convergent, plates collide or transform, the plates slide past one another. So here are representations of those three types of movement. Seafloor ridge is divergent. Convergent happens at an oceanic trench, or where the oceanic plate meets the continental plate, and then transform boundary is two plates sliding past each other. Earthquake and volcano activity related to the plate boundaries. The moving plates will shake, and subducting plates become molten and inject upward, and this is all contributing to what we call the Pacific Ring of Fire. So here are the plate boundaries. You can see volcanoes represented with red triangles. Hotspots are represented with the yellow circles with a red border. And then we have the plate boundaries, which we've seen before, subduction zones, ocean trenches, etc. You will be making a map of this data to better understand the location of these phenomenon. Hotspots are where upwelling magma comes to the surface, not associated with plate boundaries. The Hawaiian Islands is an example of a hotspot. So the Hawaiian Islands are continually forming, with the biggest island of Hawaii being the youngest. And you can see the increasing ages of Maui, Molokai, Oahu, and Kauai. And in B, you can see the eroded cliffs caused by wind, rain, and the weather elements. And then in C is fresh lava that is forming new land, reaching the sea in Hawaii. So with deformation, folding, and faulting, stress affects rock through deformation. There are different stresses: tension, compression, and shear. Tension will stretch a rock, compression squeezes or shortens a rock, and shear twists or tears a rock. Here are representations of that tension or pulling apart, compression or squeezing together, and shear moving along each other. Rocks respond to stress by folding or bending, or faulting or breaking. This depends on the rock composition, whether it's brittle or harder, which a term is ductile for harder rock. Folding is rocks are deformed as a result of compression. An upward fold is called an anticline. A downward fold is called a syncline. Warping is when it arches upward and creates basins and domes. Here's an example of anticline and syncline drawn as Earth features, and these are compression forces. And then on the right is a picture of where these forces can be seen in the Appalachian Mountains on the tri-state border of Kentucky, Tennessee, and Virginia. Faulting is when rocks on either side of the fracture move relative to the other side. This leads to earthquakes. There's normal faults, reverse faults, and strike-slip faults. Normal is where hanging walls or cliffs called scarps are formed by pulling apart. A reverse or thrust fault is where it's pushed together. The hanging wall is pushed up, and a strike-slip fault is horizontal movement, right lateral or left lateral. Lateral means to the side. So some images I want you to study in your text related to these faults. We have tensional stress, compressional stress, and then at the bottom a strike-slip fault, and some resultant images for you to look at and compare to the diagrams. Earthquakes are caused because plates do not glide smoothly past one another. There is a sharp, sudden release of energy, and this results in a seismic wave or earthquake. It most often forms fault ruptures, and the focus or hypocenter is where earthquakes begin. Directly above that point on the surface is the epicenter. The shock wave is produced and radiates outward. Aftershocks may occur after main shock. They can be just as strong as the original earthquake. This is a diagram of those phenomenon happening. So we have the focus or the occurrence of that energy release. The epicenter is directly above that with a red circle, and you can see the seismic waves are drawn in red curves here. With earthquakes, they are measured with intensity and magnitude. Intensity is how strong they are, and magnitude is a measurement of the units of force. A seismograph records vibrations of waves. A modified Mercalli scale is qualitative, from barely felt to catastrophic total destruction. A Richter scale is quantitative, or numbers, for amplitude of waves. A moment magnitude scale is more accurate for determining magnitude than Richter scale. It considers the amount of fault slippage, size of the surface area, and nature of materials that faulted. Earthquake prediction is difficult to determine precise or specific times and places. Paleoseismology is the history of plate boundaries, and another approach to studying earthquakes is looking at the measurements of past or existing earthquakes that might precede a bigger earthquake. So here is a map showing you earthquake probability, and you can see that the highest areas in the world of probability of earthquakes are shown in dark red and burgundy. Since 1900, over 1.5 million people have been killed from earthquakes, and the deaths are related to earthquake magnitude, the population density near the earthquake, building codes, the time of day, whether people are in structures or out of them, and the after effects, which can be tsunamis, fires, and debris flows. Here is a death toll of earthquakes, and you can see that Haiti has been the hardest hit. Some examples of large earthquakes. In Nepal, there was a 7.8 magnitude, and there are things called megathrust earthquakes. They occur in convergent subduction zones. The biggest have been in Japan, Indonesia, Chile, and Alaska. So just some examples of the devastation. This was an earthquake near Mount Everest in Nepal. Here's a tsunami on the left, which is a large tidal wave, and that is caused by an undersea earthquake. And then on the right, almost nothing was left of this area of Japan after the tsunami. So some more examples: Virginia in 2011 and the San Andreas Fault. This is showing you a map of the epicenters of some large earthquakes and the areas where there was reported shaking. So you can see that the areas of places where people report feeling the earthquake extends far beyond the epicenter. Here's an example of the modified Mercalli scale, showing you the reported perceived shakings, and it is shown with colors ranging from blues to reds. There are 1,300 known volcanic locations, 600 active, and these have erupted in the last 10,000 years. The distribution of volcanic activity is subduction zones or convergence zones. There are seafloor spreading centers and hotspots. Here is a depiction of how volcanoes work. So in the area of a subduction zone and other weak spots in the lithosphere, you can see the rise of magma. They are very common on the seafloor, beginning on the left. They're also on continental plates and in mountainous areas. And we have those movement of plates which contributes to volcanic activity. So the type of volcanic activity depends on source and viscosity, or how thick the magma is. Low viscosity is very fluid, high is slow moving, and thick. Think about the difference between honey or peanut butter. So honey would be low viscosity and peanut butter would be very high viscosity. It's much thicker. Here are some examples of different types of volcanoes. There's a cross-section of a volcano, and it is showing you the magma chamber, the crater, and the different structures of the lava and pyroclastic materials. We also have composite volcanoes and shield volcanoes. There is a cinder cone shown in D and a caldera shown in E. So with volcanic features, the volcano forms at the end of a vent. A crater forms on or near a summit. There's two main forms of lava, which is rough and jagged, and pahoho is thin crusts of ropey folds. A cinder cone is a hill shaped like a cone, and it's less than 450 meters high. A caldera is a large depression that forms when summit material on a volcano collapses inward. Here's some differences between that really sharp lava and the ropey lava, the A'a and the Pohoho. So volcanic hazards and monitoring are reliable indications. They often exist before volcanoes erupt, and things like gas emissions, ground deformation, and seismic activity precede major volcanic eruptions. So here are some scientists that are studying areas of known volcanoes and trying to predict when the activity will occur by observing the eruptions at the top and using tools like remote sensing, geophysical measurements, seismicity, hydrology, etc. These are recent eruption locations, and you can see that there are subduction zones and spreading ridges shown here. Those are the areas associated with the most deadly and most active volcanoes, which are shown with those red triangles. Here's an example of an active volcano in the Andes Mountain, which stretches between Ecuador and Chile. Some more examples of volcanic activity and devastation. An erupting volcano, more eruptions, and the resultant lava deposition at the bottom. And then I'm going to finish up with orogenesis. It's mountain building. There is oceanic to continental plate collisions, oceanic to oceanic, and continental to continental. So some complex diagrams, I'd like you to come back and review them. This is the process by which mountains are built, and they are the result of two plates meeting, and you can see that there are compression forces which actually push up those mountain ranges, and the forces are shown by the yellow arrows in these drawings. Faulted landscapes are pairs of normal faults that act together to create distinctive terrains. Parallel mountains are fault block mountains. Horst is an upward faulted block. A graben is a downward faulted block. Here's a horst, upward, and then a graben downwards. And that's it for this chapter. I hope you enjoyed learning all about tectonic forces, volcanoes, earthquakes, and mountains.